started. Hi everyone, my name is Rob Emanuele. I'm a software developer at Azavia. I'm a core contributor to the GeoTrellis project, and I'm a member of the PMC at LocationTech. So what I'm going to talk to you about today is a little bit about what, so that in the title there's processing geospatial data at scale. So I want to give a little bit of information about what I mean by that, right? And then give you a background on some of the big data frameworks that we leverage at LocationTech. Talk a little bit about what LocationTech is, and give you an overview of the 4 LocationTech projects that deal mainly with big geodata. So yeah, let's look at this phrase for a second. Processing geospatial data at scale. I want to parse it in a couple of ways. So when I say geospatial data at scale, what am I talking about? So to do a little bit of a bigger than a bread box, smaller than a house sort of analysis here. So for instance, Landsat 8 on AWS, right? There's a publicly available data set of Landsat on AWS. It's about 355 terabytes and counting. OpenStreetMap edit history, if you wanted to do some cool stuff with that, that's 75 gigabytes compressed. I haven't uncompressed it, but I'm sure it's much, much larger. And then Mapbox did a blog post a while ago that talked about 3 years of geotag tweets. That was about 3 terabytes. Also, for NED 1/3 arcsecond, here's a rendering I just did. I don't know what's going on with that source data. It's a source data problem over in Texas. But yeah, so this is a rendering that I did with GeoTrellis. We look at the Blue Ridge Mountains, which in this map are red for some reason, and go down to the level of detail. And this is about 500 gigs of raster data that we're rendering off of. So that gives you an idea what I mean by geospatial data at scale. And there's somebody who's here that was we want to process a petabyte of imagery with GeoTrellis. And I was like, that's a pretty big scale. So that's sort of the upper end. So I also want to talk about processing data at scale, because processing geospatial data at scale is sort of a special case of just the more general problem of processing data at scale. And yeah, there's a whole big domain of people doing that. And I want to talk about that by talking about 3 different Apache projects: Apache Hadoop, Apache Accumulo, and Apache Spark. I'm going to give a little bit of a history lesson of where the projects came from. So in order to do that, I'm going to go back to the early 2000s and talk about a project called Apache Nutch. Apache Nutch was a couple developers' attempt at making a better search engine, an open source search engine, sort of what Google was doing, but in an open source fashion. And they did a good job of it. They could set it up on a beefy server, and it worked for small data sets. But the web is huge and it's growing, so it just wasn't really a scalable solution. And then in 2003 and 2004, Google published some papers. One was called MapReduce. It was about the MapReduce programming paradigm. And the other was Google File System, which talked about a distributed file system that they had created. A distributed file system just says, hey, I have a bunch of nodes in a cluster. I can store massive data sets in there without replicating, replicating for redundancy, but without having the data set in each of the computers. But I can look at them as if they, I could reference them with one handle. So Apache Nutch, the Apache Nutch guys looked at this and said, all right, this is kind of what we've been going for. So they implement that in Apache Nutch. And then in 2006, those portions were spun out to form Hadoop, right, the yellow elephant that many of us know and love. In its early life, Yahoo was really the champion of Hadoop. It employed some of the core contributors, threw a lot of money at it, and they moved all their large data processing to Hadoop, and it was really, really successful. So eventually, in 2007, there's all these big companies that are doing their large data processing on Hadoop. And in 2008, Hadoop graduated as a top-level Apache project, which is a measure of success. So just to briefly go over an intuition about what the MapReduce programming model is like, this is the simple word count that everybody uses, right? I have a set of sequence of words. I can split them up. Say I have a 3-node cluster. These pieces of data would all be living on separate nodes. And then I can map them to the word and account. I could shuffle the data around so that all of the words and their just contribution, which is just a number 1, live on the same node, reduce that down into a count by doing a summation of the value, and then now I have my final result, which is a much smaller data set and is a summation of my source data. So Hadoop was really successful, awesome. People were doing MapReduce all over the place, and including Matej Zaharia, who was a researcher at UC Berkeley, and he had been contributing to Hadoop, using Hadoop, but he noticed that his colleagues who were working in the machine learning center were having some trouble with Hadoop based on the way that it approaches iterative algorithms. So in 2009, he created a framework called Spark. And Spark solves this iterative algorithm problem by, well, let me describe the problem first. With Hadoop, if you want to run an iterative algorithm over a large data set, what you're going to do is you're going to read that data in, do your MapReduce program, and then write the results of that iteration back out to disk. And then you're going to read it in from disk again, do the next iteration, out, read in, out, in, out. You're paying a lot of cost for that I/O. So Spark's idea was okay, well, what if we just used the memory of the cluster sort of as this distributed cache and kind of kept track of where the blocks of memory were, and then that way we could just iterate over it hot in memory, and it's a lot faster. So it outperformed Hadoop in iterative algorithms immediately. But then they realized that the people who were developing it at AmpLab realized it was a really interesting, well-founded project for doing distributed computation in general. Right? So it was open source in 2010, maintained by AmpLab, and then it was donated to the Apache Software Foundation in 2013, and graduated at a top-level project not too long ago, just 2 years. Yeah, so the way to think about Apache Spark in a general sense is that it's a distributed computation engine. And it's also an API. It's a programming API that's really great. It allows you to look at your distributed collection of data as if it were just sort of this single collection in your programming API, which allows you to do things that you would normally do to a collection, like map over the results or do a reduce function on it, and kind of treat it in a functional manner, doing functional transformations on this collection of data. It's written in Scala. It has language bindings for use with Java, Python, and R. It's got many users. It's distributors of applications. This is just to say this is a very popular framework. It's growing in popularity. And last FOSS4G, somebody asked about the scale, how much data can it handle, and it's not comparable to Hadoop. It actually really is. The largest cluster is running on 8,000 nodes, largest single job, a petabyte. There's this competition that they run I think it's every year, where they do an on-disk sort record. And Hadoop was winning it for a bit, and then there were some applications that were specifically designed to win it, and then Spark won it in 2014, which is a pretty big deal. I think it was a petabyte sort. And then so it's been growing. So this is 2014 figures, and we can see that there's a lot more contributors in 2015. I think that graph is still going up. And then you notice the note that the increase in lines of code is mostly in libraries, because Spark is not just that single distributed computation engine. It's the ecosystem around it. It's the tooling that's built around it. For instance, there's Spark SQL, which allows you to execute SQL queries against distributed data using Spark. Spark Streaming, which takes micro batches of of streaming data and process them in a distributed way, kind of with the same API as you would with data at rest, in a batch job. MLlib allows you to train machine learning models off of distributed data, and GraphX is a library for doing graph processing algorithms. All right, the next one I want to talk about is Accumulo. So a similar sort of story. Google did something cool and then published a paper. And they published a paper on this concept called Bigtable, which is a distributed storage system on top of Google File System that was an indexed version of that. With a lot faster lookup time. So immediately there's an open source, there's a plethora of open source clones, not so much clones, but just open source projects that take that concept and incorporate it, like Apache HBase, Cassandra, and Accumulo. So Accumulo was created by the NSA in 2008. It was donated to the Apache Foundation in 2011, graduated as a top-level project in 2012, and at that same year, there was actually a Senate bill that was on the floor of the Senate to defund Accumulo unless they proved that there was no other commercial viable option that had the security features that Accumulo had, and also that it had become a successful open source project. They had to prove that, and it graduated top level Apache the same year. So I think that's kind of funny. So Accumulo, yeah, like I said, it's a big table clone. The records are actually stored in HDFS, so it's like a layer on top of HDFS. But it also provides a lexicographically sorted table index for really quick range lookups. Yeah, and then so it's sort of intuitive visualization of this is if I have, my row and my column data that has a value sort of in a table form, I can partition that up, split that up, and then serve it on tablet servers that are, one or more per node in my cluster. Right, so that's 3 projects out of Apache that deal with big data, and they deal with like the general problem of processing data at scale. But what we want to talk about is processing geospatial data at scale, and those projects don't give that for free, right? So some people might be like, oh, there's like lat long, and then there's 2 doubles, right? And that's geospatial. But we all know that that's not true. Like, we want to do bounding box queries. We want to do complex geospatial operations. So how do we end up doing that? One answer is that we're talking about today is these 4 projects that sort of layer on top of these Apache Foundation projects that provide, that enhance, that enable these platforms to operate in a geospatial way. And all 4 of these projects have a home at LocationTech. So I'm going to take a moment to just talk about what LocationTech is. If you don't know, LocationTech is a working group inside of the Eclipse Foundation. Eclipse Foundation is an open source foundation that hosts many projects and provides services to open source projects. So the working groups, there's like one focused specifically on scientific software. There's one focused on Internet of Things, and then LocationTech, which focus on geospatial software. So here's a list of projects of LocationTech. There's the 4 of them that I'm talking about today are the ones that like really focus on like the Apache big data platforms, but we have a lot of other ones. People that do anything in Java might know JTS as like a godsend for doing anything vector on the JVM. But I'm going to focus on these 4 today. The first one, GeoJinni, formerly called Spatial Hadoop, a really descriptive, awesome name, but legal reasons. We'll change it to GeoJinni. So what GeoJinni provides to Hadoop is a spatial language, so we can start talking about points and rectangles. You could do these queries in PIG, a DSL for running MapReduce jobs. It gives you built-in spatial data types, so you're not just storing like a lat and a long. You have like complex geometric data types. It provides some spatial indexes, which we'll go over in a second, and spatial operations. So whenever we talk about like big data, geospatial processing, the conversation quickly turns to how do we index the data, because a lot of database technologies work with one-dimensional indexes, but when we get into spatial and spatiotemporal, we get to 2 dimensions, 3 dimensions, n dimensions. So GeoJinni actually solves it in a way that the 3 other projects don't. What it does is it takes a coarse grid of the space, and then for each of the grid cells that you have, it stores a file, like a Hadoop file. I think it's a sequence file that stores that file in a distributed way. But it also stores an index, like sort of a traditional R tree or KD tree index that it first reads in order to find the offsets into the sequence file to pull out your points. So that allows you to do pretty quick spatial queries on your data sets. And it provides a variety of different indexes that you can store with your data. So just to give you a sense of what this thing can do, 1 trillion points generated in 3 hours on a 10-node cluster can generate a heat map of temperature over spatiotemporal data. It can also generate videos, so you feed a bunch of spatiotemporal data, and it generates heat maps, and then what you get out is a video so that you can watch. I think this is temperature over Saudi Arabia. Great. So, yeah, if you're working in Hadoop, specifically, you're not like trying to deal with Spark or Accumulo or any of that stuff, and you want to do geospatial stuff, take a look at GeoJinni. It might be a great solution. Next one I want to talk about is GeoMesa. So a really generalized, like unfair thing to call GeoMesa but kind of like it's at the intuition of a core functionality of it, is it's Geo plus Accumulo, geospatially enabling Accumulo, and accessing that through GeoServer, right? So with GeoMesa, you can do things like in a web application, actually do a polygonal query of point data, filter it not only by the spatial, but also by the properties of the simple features. It provides a GeoTools data store, so you can actually access it through tools like Python, do things like kernel density analysis of the point data, also visualization of spatiotemporal data. Another really cool thing that the GeoMesa team, the CCRI team, is doing is working with stream processes. So the two other projects that I haven't even mentioned are Apache Kafka and Apache Storm. So Apache Kafka is like a distributed pub-sub messaging platform. And Storm is a streaming processing engine for building up topologies of inputs. You build up processing things called bolts, and then you can pipe that data to a variety of places. So, for instance, say I was a shipping company, and I had a bunch of ships worldwide, and I wanted to track their positions, and they had GPS data, they had sensor data coming back at me. I could funnel that all to a Kafka queue, right? And then end up processing that stuff, pulling that off of the queue, processing it in Storm, where maybe I'm parsing out some data, I'm enriching the data with some other qualities, maybe the ship name, maybe the cargo, whatever. And then I could store that directly into Accumulo, and then using GeoMesa's plugin for GeoServer, I can visualize that data, right there. I could also throw it into another Kafka queue and visualize that through their plugin, their Kafka plugin, the GeoServer, which will actually end up being quicker because I don't even have to ingest it into Accumulo. And at the same time, this is all happening at the same time, I could get Spark Streaming to be listening to the Kafka queue, do some analysis, say like, when in the last hour 2 ships have been within a mile of each other, throw that in Accumulo and visualize that through GeoServer. So we're visualizing 3 different layers, 3 different cuts of our data at sort of different streaming intervals based off of the topology that you can build up with tools that the GeoMesa team is building. Another cool thing they're doing is integrating with Spark SQL. So Spark SQL, you can, like I said, you can throw SQL at it and do cool stuff. But they don't understand what a bounding box is, right? So what GeoMesa will do is it'll actually parse out that geospatial portion of it, perform the query against GeoMesa, and now have an RDD, turn it into a data frame, and then perform the Spark SQL query against it. So you get the total filter. Great. Next project I want to talk about, I know I'm going quick, I'm sorry, I don't have a lot of time, is GeoTrellis. This one's near and dear to my heart because I'm a core contributor. So GeoTrellis is a Scala library for doing basically all things geospatial in Scala. If you're using Scala and doing geospatial stuff, you should take a look. We have things like a wrapper around JTS that allows you to do a lot of stuff with vector data. It enriches JTS a bit by allowing you to parse GeoJSON, write out the GeoJSON, do reprojection using Proj4j. Also, with rasters, we can reproject rasters, do all sorts of map algebra operations. We sort of started with raster, so that's probably the most complete portion. And then we take that functionality and kind of move it to Spark. So we have the ability to take, read in large GeoTIFF, layer of large GeoTIFF files, chunk it, turn it into tiles, reproject it, and then save it off into in an indexed fashion into HDFS, Accumulo, or S3. And there's a pull request for Cassandra. Also, we released 0.10, so that's been long coming. So if anybody was waiting on that, we released. You should use this. Here's some cool stuff that we're doing at Xavier with GeoTrellis. So here's a flood model based on rainfall. It's like a bathtub model of like the water depth based on elevation data, cropped by a polygon. This is sort of a histogram of NLCD data that you can draw polygons and see the result. And then so, the basic technique that GeoTrellis has used for raster data is, when you have large raster data, you just chunk it up into tiles. If you have large spatiotemporal raster data, you chunk it up into tiles, and then you have stacked tiles. So you have like a 3-dimensional index of this tile data. So when you're doing things like polygonal summaries, right, when you do a query to fetch the data that you need in order to do the intersection, et cetera. You only have to pull back the tiles that you need, and because they're indexed with a space filling curve, that bounding box query is very fast. All right, so this is something I did recently, just to throw some numbers up on the board. So I rendered elevation with hillshade and also combined it with NLCD to render rivers. And I was using 100 spot instances on M3 extra large. So spot instances are the way to go because, look, they're 4 cents an hour, where the one master that I have is an on-demand instance is 26 cents an hour. So I have about 400 CPUs. And the EMR cluster charge you like 7. So EMR is Elastic MapReduce. It's a really awesome AWS service. Talk to me later if you want to know more. So this is like less than $5 an hour of a cluster. So Spark provides this really cool UI when it's chunking through jobs. So this is, up here is a visualization that it gives you of what's called the directed acyclic graph of computations. So we're doing these things like mapping values and joining and flat map. And this is kind of give you an idea of like the complexity operation. It actually goes way over there. And then this complete stage just gives you the shuffle read amount, which is over a terabyte. Oop. And then so this is when the job completed. We can see the total uptime was a little over an hour. And that's for taking the raw NLCD data that's in GeoTIFFs and the NLCD data and combining them and rendering them. So just to show you, this is probably ill-advised because the connection hasn't been very nice. But this is, I just saved the PNGs to S3. And so this is like a ZXY service, but it's just PNGs being pulled off S3 after I ran that job. And this is a result of the job, right? It's the elevation data colored via some color ramp, and then there's just an algorithm for taking the hillshade value and then replacing it into the HSB color space, so you get that cool hillshade effect, and then just wherever it's water, just paint it blue. Cool. All right, next one I want to talk about is GeoWave. So GeoWave produces pretty maps like this. This is GPS data. There was a talk about visualizing big data using GeoWave. Hopefully you caught that. Catch the video if you didn't. Yeah. So one unfair overgeneralization of thinking about GeoWave is that it geospatially enables Accumulo and accesses it through a GeoServer. And if I sound like I'm repeating myself, I kind of am. There's a core functionality about the two that really overlaps. And it's sort of a case of parallel invention. Right? GeoMesa was being open sourced while GeoWave was like about to be open sourced. So they sort of serve a similar function, but there's actually some stark differences. The top line is the starkest difference, but we'll skip over that one for now. There's various backends they support. They both support Accumulo as their main backend. They both have H-based support that's like sort of experimental. GeoMesa has DynamoDB and Google Cloud Bigtable support, which I think is really cool. If you're using MapNIC, you might want to check out GeoWave because it does have MapNIC support. There's a difference in like the processing frameworks, although there is a Kafka ingest for GeoWave, so I should have put that on. And then a big difference is that they're both JVM languages, but one's written in Java and one's written in Scala. And that makes kind of like figuring out how you can tool them together a little tough. But you can run these things on the same Accumulo cluster on two different tables. They're not mutually exclusive. So the index type is sort of the big difference here. GeoWave was developed as sort of a general and dimensional indexing scheme on top of Accumulo, with spatial and spatio-temporal being the case that is actually like used. So it's the use case, but it actually supports n dimensions. GeoMesa has the z-order curve, so the Hilbert versus z-order curve. They're just two different space-filling curves, but provides spatial and spatio-temporal support. And then the two things, the tiered indexing and binning, are two features of the Accumulo index that GeoWave supports. There was a talk earlier today by Eric Robertson that's really great to check out if you want to learn more about space-filling curves. But there's this idea of tiered indexing. This polygon would cover 66 cells, but if we have a multi-resolution space-filling curve, we can actually store less duplicates by storing polygons in an appropriate tier. And then binning is this idea of like having unbounded dimensions like time so that you can have a space-filling curve that like fits in year 1, year 2, year 3. GeoMesa actually provides binning support, but specifically for weak, whereas the GeoWave binning is sort of for arbitrary dimensions. All right, but we're all at LocationTech, so we're all doing these space-filling curve projects, right? And but we're all at LocationTech, and a large part of what LocationTech means to me is the collaboration element that happens there, because. And I feel like it's hokey to just throw a definition up and like talk about it, but I didn't know about the second definition of collaboration, where it says it's a traitorous cooperation with an enemy, right? And if we were like competing companies, like these projects are kind of being developed in different levels by different companies. So if we were like competing companies, that would be, if we were to collaborate on our software, like that would be traitorous. Like my boss would be really mad at me. But we're open source, and we believe in those ideals, and we believe in the ideals that as we all sort of like define and push forward the cutting edge of what exists in the open source field, we all benefit from it. And I don't want to do work that somebody's already doing better. So we invent things like the SF Curve project, which Jim Hughes will be talking about in the talk directly after mine, which is a collaboration of the GeoTrellis, GeoWave, and GeoMesa projects to try to figure out what is the best way to do a SF curve, a space-filling curve on the JVM. Right. So at LocationTech, we're learning to collaborate. It's hard. We have projects that do the similar things, but they're in different languages, and we're kind of like solving similar problems. And collaboration is just a hard thing to do, but we are getting better. And LocationTech provides us a place that gives us a hub to connect to, so that it allows for those collaborations to happen. So if you have big data problems, if you're working with big data, please join us, get involved. Just join the mailing list and talk about your use cases, because we want to hear if you have better ways. If we're totally off base, like tell us so that we can do the best thing possible. Or if you have questions and just want to get involved, like let us know. Also, if you have projects, you can propose new projects on the LocationTech website. Thanks. Oh, okay. Yes?
So if I'm dumb. So if I were going to be, I'm running a simulation model and I'm streaming a whole bunch of data in,
Yeah.
which project am I picking? You gave me so many options.
Yeah, so many options.
Like, I can tell I don't want Hadoop, because that's not Hadoop's. Like, streaming data,
Yeah.
it is not Hadoop. So we can lock that part of the universe off.
Right.
And so it looked to me like what I wanted is GeoMesa, because I could back that with Cassandra.
Yeah, so the reason I'm pausing is that the streaming support for any of the projects, I think GeoMesa has the most capabilities for that. But you're still kind of using, what you'd be using is Kafka and Storm and Spark streaming, and then relying on some tooling that's provided by some of the projects to do the geospatial part of it. So if you're trying to throw them into a data store, if you want to do, Accumulo can take fast writes. So you could use any of those projects that are just writing directly into Accumulo. And then once you have those in Accumulo, if you wanted to do Spark jobs over it, then like GeoTrellis might be an option, especially if you're doing raster data, or any of the other projects, really. So yeah, sorry there's so many options.
So what it sounds like is the Accumulo is for the fast writes. For a generic solution, Accumulo for the fast writes, and then pick one of the LocationTech projects that meets the needs for the analysis on the way out.
Sure. Yeah, totally. And like if you're trying to access it through OGC standards, you would use the GeoServer plugin of GeoWave or GeoMesa in order to like see it on a map. And if you're using Spark, yeah, I would say GeoTrellis. And then as Cassandra support matures, that'll just be another option. If you want to store your data in Cassandra, we'll be able to store it in that. And I'm not even sure which is the most mature Cassandra support at this time. I'm looking at Jim because he's the GeoMesa guy.
Yeah, that's a fair question. So, yeah, I mean,
cool.
we've had a good chance to do a proof of concept for Cassandra. So, I think for any of them, if you've got to pick what backend to use, if you go with Accumulo, that's going to be the lowest risk. If you're wanting to jump into one of the other ones, you might need to bring a little elbow grease.
Elbow grease will be necessary for all of this. If you're working with big geodata, do not try to get into big geodata if you don't have any elbow grease.
I hear GeoTrellis is really easy to use.
Other questions? Yes.
For GeoTrellis, you mentioned S3 support, and I think the example you gave writing out PNGs as a result of that process, if there's a possibility for you to use them from S3 and then do analysis. Or is that something that I
Yeah, so, oh, I'm sorry. So the question is, for the S3 backend support for GeoTrellis, we were writing out PNGs to S3. Can we read in GeoTIFFs and do some analysis there? The answer is totally yes. Those rasters existed on S3 in GeoTIFF format, right? The NED data, we got off a Stamen who chunked it out into GeoTIFFs of like 10,500 by 10,500. We have a format that actually stores in S3 that's like an Avro-encoded indexed format that's way quicker to query, because if you have GeoTIFFs, you're like doing like you have the extents, you don't know if they overlap. If you were to tile and reproject and get in the projection you wanted and then store it off in S3, you could store that into what we call like a layer that has the space filling curve indexing, and then those things are just on S3. You could write a tile server to then like serve out the individual tiles very quickly, or start to, when you create an RDD and try to do analysis off of it, you've already done all that pre-processing of reprojection, tiling, indexing. But you could just from the start, like that job that I did was from the start, GeoTIFFs, and then doing the hillshade calculation, doing all that stuff, and then my end result could have been I could have outputted GeoTIFFs. I could have stored it in a GeoTrellis layer, but I chose to render PNGs and then throw them up on S3.
With that Avro approach, are you duplicating data or is it pointer?
What's that?
With the Avro approach you just mentioned, is that creating a duplication of that data with the actual pixels?
Yes.
Or is it
Yeah. Yep. Sorry. So the Avro encoding. Sorry. The Avro encoding, the GeoTrellis layer, when you save it off, that is a duplication of the data. So if you're not willing to pay that price to have an indexed version of your data set or have that be like the authoritative version of it, you're going to end up going with the raw GeoTIFF. Any other questions? Okay, ended early. Awesome. Thanks. Last minute.
Any of this stuff is Dockerized yet?
Yes, ish.
Because I was just looking at Accumulo quickly, not that I wasn't paying attention to other people's questions. But
I have my backup slides.
on my Accumulo, it looked like there's like 4 different pieces you have to actually install to bring up an Accumulo.
Yeah, it sucks. So our Moscow friend Gregory Pomachin, is working on this project called GeoDocker Cluster, which is a series of Docker images that just containerizes Zookeeper, containerizes HDFS, Accumulo, and GeoTrellis, GeoMesa, and GeoWave. So that's currently happening. He's also already got Cassandra support. He's killing it. So he's all about, like, before we hired him, he was like sort of just in the open source, like in the Gitter channel, and he was like, oh, I had this like 7-node cluster I've had up for 5 months that I deployed all this stuff via Docker that chunks through Landsat imagery, and we were like, oh, you want a job? So yeah, he's currently working on that, and I'd point you at that if you want a Dockerized version of Accumulo. So other things we're doing with this is like standing up an EMR instance which doesn't have Accumulo installed, and then installing Accumulo, like it already has Spark and Hadoop and stuff, but it's installing Accumulo via Docker containers on top of the EMR cluster so that you can actually use Accumulo with EMR. Any more questions? Are we sure? Oh, there it is.
So next week, you're going to give the same presentation to Apache Big Data.
Similar, yeah.
Similar one, which I applaud. And the collaboration, as you said, in terms of definition number 1, is a tremendous thing. Is there things that you want to take to that community, the
I think getting us on their map makes sense because they're not necessarily thinking about geospatial. And if you go through the the question was what should we be asking of the Apache community? We're relying on them so much. Like, what can we be asking of them, or how to collaborate with them? If you look at the Apache Accumulo mailing list, like there's like every once in a while a talk about like how can you do like bounding box queries or space filling curves on Accumulo, and somebody from the GeoWave folk will like answer it and sort of collaborate in that way. But I don't think that we're necessarily, that use case is like very big. And I think it's growing, as is an example of that at Apache Big Data, there's going to be a geospatial track, and we're going to be talking about it and getting projects together and saying, okay, we use Apache products to do big geospatial data. What are we doing here? How can we collaborate? And I think that's really great. Also, a collaborator, Eugene, had submitted patches to Accumulo, so that's one way to collaborate. We're kind of trying to send back code up their way since we use their code so heavily and rely on it. Yeah. All right, that's it. Thank you so much.